afternoon, everyone. Good afternoon, good evening, good morning, wherever you are in the world. My name is Long Fan. I'm the application engineering manager at Wilo American Marsh Pump. I will be today. We have the agenda for today is we're going to talk about what is a vertical turbine pump is, and then we will explore different markets and applications. We're going to look at different vertical turbine types and their major components. We'll have a little practice on how to select a vertical turbine pump. And finally, we're going to deep dive into detailed components of the vertical turbine pump. So by attending this webinar, I hope you will able to understand and recognize vertical turbine pumps and evaluate different applications, different systems requirements, identify the key components of it, and then apply the fundamental principles for a proper sizing of these pumps. So first thing first, let's define what is a vertical turbine pump. So according to Hydraulic Institute, which is a very prestigious agency for pumps industry, they define vertical turbine pump is a vertically suspended pump within the rotodynamic centrifugal pump. In this centrifugal pumps family, you have other pumps cousins like overhang between the bearings, regenerative turbine, and circulator. So the vertical turbine pump has the way they call vertically suspended because where the impellers are mounted on a vertically suspended shaft and closed within a bowl assembly. They designed to efficiently move fluid from below-grade sources. So let's look at the operating principle. It's very simple, right? Water enters from the very bottom of the pump through the suction bell, the suction inlets. As it moves through the stages, the impeller will increase the velocity by adding energy as it moves upward. The bowl assembly converts this velocity into the pressure head. The water then exits out into the column assembly and exit out at the discharge head, as you can see at the last picture. Before we talk about how a vertical turbine pump works, it's helpful to understand why this pump exists and how it has evolved over the last century. Vertical turbine pumps first became popular in the early 1900s for the deep well application. Community needed a reliable way to lift groundwater from hundreds of feet below the surface. And the vertical turbine pump design was ideal because the pump bowls could submerge while the motor remained at the ground level. From the 1920s to the 1950s, as agriculture expanded, especially across the western United States, vertical turbine pumps became a preferred irrigation pump. They could move very large volume of water efficiently from rivers, canals, wells, helping support large-scale farming. From the 1950s to the 1980s, with rapid industrialization and growing cities in the North America and around the world, the application expanded beyond irrigation. Vertical turbines become common in municipal water treatment plants, power stations, cooling water systems, flux control, and many industrial processes where high flow, reliable operation were required. So from the 1980s to the present time, today, vertical turbine pump built on the same basic hydraulic principle that lasts over a century, but with a significant advance in efficiency, materials, and controls. The modern design improved hydraulics, corrosion-resistant materials like stainless steel and duplex alloys, variable frequency drive for energy savings, and smart monitoring system for predictive maintenance or greater operational flexibility. So while the technology has evolved over more than 100 years, the fundamental purpose remains the same, moving a large amount of water efficiently and reliably. Now, let's look at what makes a turbine pump different from other pump types. Within the family of centrifugal pumps, I'm going to let's look at a few highlights of the vertical turbine pump as compared to other cousins within the family here. So the vertical turbine pumps have flooded suction, both fully submerged. The motor typically above the liquid. It can provide very high head thanks to its multi-stage design. The flow capacity could be from the wide range from low to very, very high. The footprint is small thanks to its vertical design, and the motor main axis is above ground, typically. No concern much on the APSA. These pumps are very efficient, moving large amount of water, and they can use in wide range of applications from municipal irrigation, industrial cooling water, and so on. Some of the advantage of the vertical turbine pump as compared to other pumps within the centrifugal pump family is they basically have no practical suction lift limitation. They are very ideal for deep wells and wet pits, smaller installation footprint, and provide high flow, high head, and the motor remain above the liquid. Therefore, it's allow easy motor maintenance and replacement. Finally, they are available in extremely high capacity design as compared to others. So in this section, next section, we will explore different markets for an application of these pumps. These pumps are widely used in agriculture, industrial, and municipal. They are typically open or enclosed light shaft. They can have specialized material for aggressive environment like seawater. They can also use for high pressure applications like high-rise building in big cities. From an application standpoint, let's look at the surface water. So these pumps is useful for surface water, from moving from open pit mine dewatering to raw water intakes from river, lakes, ponds to help cities and towns to recover water in water recovery or water treatment plant. The next application, but also important application of this vertical turbine pump is extract groundwater through deep wells like one you see from underground aquifers and dewatering process. The vertical turbine pump can also use for pressure boosting. They use to transport water from great distance or great depth while boosting the pressures. From a market point of view, these pumps are initially designed from our history brief that we know that it's designed for agriculture, municipal groundwater. The two types of pumps used are enclosed light shaft, deep set, and submersible vertical turbine pumps. In remote area where electricity is not available, they typically use gear drive coupled with diesel engines, as you can see on this picture. The next market is industrial process. The pump can be used for industrial process water supply, raw water intakes, hydrocarbon oil boosting and transport, commercial fire protection, power generation, to like special industrial process like to deal with seawater, desalination, seawater intake, fire protections. Because of these aggressive environment, they require to have typically, have an enclosed light shaft to protect the shaft from corrosive and abrasive fluids. They typically specialize material like stainless steel or duplex stainless steel. If you have a cast iron, you have special coatings because you are dealing with aggressive fluids. They are also used for the booming mining in America for dewatering, processed water feed, raw water intake. These pumps are great for these mining purpose. For commercial building services, they also use for cooling tower, condenser water circulation, HVAC systems, chiller feeds, water cooling, especially in the AI booming today. These pumps are typically getting more traction and popularity in the commercial building services. It can also help in high-rise building water for big large cities. And last but not least, these pumps are specifically very useful for municipal and clean water. The two types of pumps that are used in the municipal And clean water is an open line shaft or can vertical turbine pump. When do we use an open line shaft for these municipal markets? Typically, it requires a lot of open summer well, the submersion depth and pump replacement are critical in scenario where you don't have enough net positive suction head available. We have to rely on the can line shaft vertical turbine pumps because these can barrels are designed to create its own sum and boosting the available MPSH. And yeah. So in this section, let's look at different types of vertical turbine pump. I have a little schematic here to show different types of vertical turbine pump configurations. In general, we have 5 vertical turbine pump configurations. Really, we just have 2 big major ones. The one is we call line shaft vertical turbines and the submersible vertical turbine. The first 4 pictures that you see is basically fall under the line shaft vertical turbines. And the last one is a submersible turbine pump. The key difference is for the line shaft versus the submersible vertical turbine pump is the location of the motors. In the line shaft vertical turbines, the motors is located above the surface, whereas in submersible vertical turbine, the motor is submerged in the water. So within that line shaft, you have open line shaft, enclosed line shaft, the fabricated can or barrel, the axial and mixed flow. We'll in the later slide, we'll look at each different subcategory and see how they use for different applications. For the line shaft vertical turbine pump key characteristics, they all have vertical shaft configuration, and you can see obviously they have single stage or multi-stage construction. The impellers typically submerged in the pump fluid. The driver typically above the fluid, right? That's the key difference with the submersible. The impellers are available in radial, mixed, or axial flow designs. They are very ideal for high head, high flow, low MPSH applications, and especially they are super ideal when suction lift is impossible and impractical. Like your horizontal centrifugal pump, they cannot do these suction lift, but this pump can. So they are that unique feature of this vertical turbine pump. Now, let's look at a very, very general anatomy of the vertical turbine pump. From the very top, you will have the motor or driver assembly. Then you will have the discharge assembly B. And you will have the column assembly to connect the bow assembly E. And then some special components like the line shaft bearing D, the impeller F, and the suction barrel strainer inlet. These are very general anatomy. We'll look into details of the assemblies as we move on. For the line shaft vertical turbine, the line shaft vertical turbine really rely on the vertical shaft to transmit the power from the motor drive above the ground, transmit all the way to the impellers located below the water surface. Right, so that's the key principle there. These line shaft vertical turbine capability can go up to 30,000 GPM, max head of 1,000 feet. In some special applications, they can be extended, but these are typical flow and head thresholds. The bow diameter runs from 5 inches to 42 inches. Can have different class of discharge flange, like 125, 150, or 300, depends on the pressure limits. The sealing arrangement can be available in pack or mechanical seal. If you have allows leaking, they use pack, and if you have a water type requirement, then you have to rely on the mechanical seals. These line shaft vertical turbine are available in enclosed or semi-open impellers, or even open impellers for axial mixed flow. So in the subset of, we call this line shaft, remember the picture where you have 4 different types subset, you could call deep set, enclosed line shaft, or lubricated, a short set open line shaft, water lubricated, or a can vertical turbine pump. They all line shaft vertical turbine pump. So in a typical 60 Hertz curve for this kind of pump, you see the envelope that covering the flow and head, flow or the x-axis and the head in the y-axis, typically the envelope is very, very wide range. So it shows us that these pumps are very suitable for a lot of design conditions. In this typical one is a Wilo vertical turbine pump is presented here. Now let's look at the difference between an open versus an enclosed line shaft within a line shaft vertical turbines, right? So the key is the bearing lubrication method. On your left side, you have an open line shaft. The pump fluid lubricate the shaft bearing because it's open to that moving fluids. On the right side, you have the enclosed line shaft. The key difference is the bearing are enclosed within a tube assembly, and you can see here tube assembly and lubricated by the oil as it drifts through this shaft and or another external lubricant. Now, we also hear about the deep set, short set. What are these terminologies mean to us? So basically, they refer to installation depth. For a deep set, you typically have a long setting depth greater than 50 feet. So therefore, it's very suitable for municipal water wells, deep wells, agriculture irrigation wells, and groundwater extraction. The short set is typically have a shorter line shaft length, less than 50 feet, and it's therefore it's typical application in cooling water systems, industrial, wet wells, municipals, surface water intakes, for example. So the third subcategory within the line shaft turbine is fabricated can line shaft turbines. When do we use a fabricated can turbines? We use, I don't know why I keep flipping. We use the fabricated can turbines. I'm so sorry. I don't know why it's keep flipping. The fabric can turbine is used. What's going on? The fabricated can turbine is used when you don't have enough sufficient available MPSH, right? So these cans are designed to create artificial flood extraction condition for the pump, right? So it will provide the boosting the available MPSH, the net positive suction head. And we use this can especially when the liquid source cannot provide adequate submersion for standard design. Now, the last type of pump within the line shaft turbine is we call mixed or axial flow vertical turbine pump. Basically, these pumps are the focus is on the more flow and low to moderate head. I'm sorry, I don't know why it's keep flipping. Let me get out here. A technical difficulty there. Go back. So the mixed flow and axial flow is, like I said, the flow rate typically high to very high. That's the focus. The head is normally low to moderate. Remember the first three category of the line shaft vertical turbine pumps are deep set, short set, and can turbine. They all radial flow, so the focus is on more pressure. With mixed flow, it's kind of be balanced because of its mixed flow vane design. And the axial flow is basically a impeller style, so it's optimized for maximum flow. So the mixed axial flow, more information for us is it can go to 30,000 GPM, max head of 75 feet, and the bow diameter running from 8 inches to 30 inches. They are normally have open impeller designs and typically 1 or 2 stages only. All right, so just a little reminder of the two major vertical turbine configuration, right? You have line shaft have 4 subcategory of open line shaft and closed line shaft, can turbines, and mixed and axial flow, and then the last one is submersible, right? So the key difference, and I repeat again, just the motor location. The line shaft is above ground, and the submersible vertical turbine pump, the motor will be underwater. So for submersible vertical turbine pump, the bow assembly really resemble the line shaft vertical turbine pump. The only special difference is the motor submerged underwater and coupled directly to the pump. So with that, there's no need for a light shaft columns. So eliminating the need for any light shaft or any light shaft bearing, anything like that. So the water moves through the intake, go to the bowl assembly, up to the columns and discharge to the discharge elbow top. Put them together side by side, you can see that obviously the motor locations are the key difference for the submersible versus the light shaft turbines. The submersible turbine have direct couple, therefore we don't need any shaft bearing or columns or light shaft. Light shaft. We do need columns, sorry. Maintenance access is for the submersible pump and motor must be pulled, right? Because the motor is submerged in the water, there's no way you can service without pulling the pump motor. The light shaft vertical turbine easy motor access is located on above ground for easy maintenance. The installation footprint minimal above ground, larger above ground, right? And regardless, these pumps are excellent for well applications, of course. A little bit more information on the submersible turbine. You can have flow a little bit up, limitation up to 8,000 because you have smaller, designs and smaller bowls. Maximum head to 1,000 feet. Bowls diameters running from 5 inches to 20 inches. And basically, the submersible turbine pump various, it resemble a borehole pump, such as the one on the screen. So the motors on the bottom, and then you have the bow assembly, and everything move up to the top through the column and discharge elbow. So to put into a summary for all types of configuration that we just learned so far. So we have open and closed, we have can. So the open and closed is the focus is more on the deliver high head, wide range of flow from moderate to very high flow, from low to high. The can barrel is typically useful when you don't have enough NPSH, or the can barrel can create its own some. Mixed flow and extra flow, the focus is more for to deliver more flow, low to moderate head, and submersible pump is the key feature of the motor located directly in the fluids, therefore no light shaft required. Let's take a look at major components of these vertical turbine pump. So first, let's look at the light shaft vertical turbine pump, right? You have we have the motor and discharge head assembly on the top, and they have the sealing assembly, the column assembly, the bow, and then suction to move from the very top down. So first, let's look at the motor and discharge head here. So on the screen here, it's showing open light shaft and closed light shaft. Remember, open light shaft and closed light, they all light shaft vertical turbines. Just the method of lubrication, bearing lubrication here, right? So you have on the enclosed light shaft, you will have a tube assembly that there. They have the motors on top. Both of them have motors. The adjusting nuts is there to show, depends on the types of motor you are selecting. If it's a vertical hollow shaft, you will need adjusting nuts. And for vertical solid shaft, you don't need it, and typically go with a shaft, and you don't need a head shaft either. In this case, we're just showing one typical vertical hollow shaft with an adjusting nut with a head shaft for the open light shaft. The sealing arrangement there, stuffing box, and then on the enclosed light shaft, you have similar components, but rather the sealing arrangement is rely upon the tube tension kit. And then you have extra feature like the solenoid oiler to basically an oil reservoir to supply oil that lubricate the spiral groove inside the shaft by gravity. Now let's zoom into the sealing assembly. For both open and closed light shaft, like I mentioned earlier, the only thing different is on an enclosed light shaft, we're going to rely on the tube tension kit, which include the tube tension nut, the tension plate, and then you have that solenoid oil line coming from the oiler, and then closing tube right below it. Everything else on the open light shaft, you have the seal housing, like in this case, we just show one example packing box, a mechanical seal. In this case, a packing box with a bronze solid bushing there, bronze packing gland, and assuming this is a vertical hollow shaft, we will need a head shaft. Down to the column assembly, you see here both open line shaft were showing alongside with the enclosed line shaft. The open line shaft, they share similarity in principle, right? You have a shafting there. They have the columns, and you have some kind of retaining mechanism for the open line shaft. You have bearing retainers with bearings. And then on the enclosed line shaft, since you have an extra tube assembly that the shaft is enclosed fully inside, you will have some mechanism to support these tubes, to support spiders, and then enclosed line shaft bearing. For the bowl assembly and suction inlet, these open line shaft enclosed really sharing the same thing. So as you see here, enclosed side, we don't want to repeat again, but they all share similar components like discharge bow, the pump shaft, or the bow shaft, impellers, intermediate bows there, sand colors, lock collets. It depends on the impeller side. It could be collets or key, in this case, assuming if the collet is a small size. And then we have the bottom, they are either strainers or tailpipe or any types of strainer to block any lost debris going through the pump assembly. Lastly, we look at symmetrical or vertical turbine pump, right? These pumps are separate from the live shaft turbine pump. So the bow shaft assembly is similar to the live shaft, except you have on the top, you will have a columns, and then discharge elbow surface plate. On the bow assembly, similar, you have a cable guard so that you can introduce cable down to connect the motor, to power the motor. The motor will be connect directly to the pump through motor bracket and motor couplings there. And the motor assembly is the one that showing on the very last there. Hermetically sealed, so that water will not go inside and damage the electrical components. Vertical, in this section, let's have a little practice on so now that we understand, different key components there, how do we select a vertical turbine pump? The pump selection criteria really rely on both general and specific requirement, right? In general requirements, we will have to ask ourselves, what will be the total column setting depth be? What is the depth of the water level, right? What is the total pump lift? The answers to these questions are vary from application to applications. Therefore, we cannot rely to calculate the head just based on the pressure required at the discharge head to the piping system, but rather at the pump discharge assembly. And specific requirement, definitely from top down, requirement had to be flow and head. We'll show how to calculate the total dynamic head in the next slide. Some others requirements such as the horsepower available, the pumping level, the net positive suction head (NPSH), the pump efficiency required, and finally the minimum submersions to what's the required minimum submersions that avoid vortices into the pump bowl assemblies. So how do we calculate total dynamic head? So again, I said total dynamic head cannot just rely on the pressure required to discharge, but rather it needs others component like the pumping level. The pumping level is basically your static level, and then the drawn down when the pump in operation. We also need to account for column friction as the water moves through the columns assembly. When you add all of these up, you will arrive at the total dynamic head for your pump system. Now, how to roughly select a bowl and stages? For just a rule of thumb, the bowl size determines flow, and the number of stages will determine head. The bowl side will influence, the flow capacity. You will give you each bowl side will give you a flow capacity range, a hydraulic efficiency range, and a pump operating range. And then the number of stages will influence the total dynamic head, the motor horsepower requirement, the shaft flow, and so on. So from manufacturer to manufacturer, they have different designs. So both sides will have typically a typical flow range. Look at this table from 6, 8, 10, 12, and 14 inches. They have different flow range. And as the both side goes up, you also have a flow range larger. So let's have a little example here. Let's say our requirement for flow is 2500 GPM and the total dynamic head is 300 feet. How do we select a bowl here? So by just looking at the table, you will eliminate the 6 and 8 inches because they are nowhere near the 2500. So it got to be above 10. But what size we want to choose? Typically, we want to run our condition near the BEP or the best efficiency point. In this table, you see 10, 12, 14 inch. For our example, 25 GPM will have 85% at 12 inches. So that's our selection there. It's the closest to the BEP point. So we're going to select the 12-inch bowl because it's closer to the BEP point for our operation. Now, let's look at determine how many stages we need. Remember, the state is determined, the head, right? So each stage add a specific amount of head to the fluid. Each stage consists of one impeller and one bowl, right? In this example of 12-inch size, you have 25 feet per stage. So if you have 4 stages, you just do the math. It's 100 feet. 8 stages, 200 feet. So for our example, you require 300 feet of total dynamic head. So how many stages? Do the math. To take 300 divided by 50 feet per stage, you arrive at 6 stages for the 12-inch bowl. Voila, then we have it. We have the 12-inch bowl, and then we need 6 stages for our specific example. Another way to calculate the total stage required is look at a manufacturer curve. Let's give another example here. Let's say we want our required flow and head at 530 GPM at 300 TDH. We look at manufacturer curves such as the one here and American Marsh pumps. So we pick out after going to different model, and we see the 9HC model is a great candidate because the BEP point is right at our required flow of 530 GPM on the x-axis. And if you go to the y-axis at the head, you see it's 45, and this curve is per stage, so 45 feet per stage. If our example need 300 feet TDH, then we do the math, we divide by 300 divided by 45 feet, we'll arrive at 6.7. Well, then we'll have to route it up to 7 stage for safety. So there you got 9HC as 7 stages. Also, on a manufacturer curve, you can also see the horsepower per stage. In this case, it's 7 horsepower per stage. Then you can estimate with 7 stages, you have roughly 49 horsepower required for your condition. We've gone so far, and we learn different market application. We learn different configuration type of vertical turbine pump. We practice how to select a basic and estimate the both size and number of stages and require horsepower for those stages. Now let's deep dive into the detailed components and understand further. So on the very top, you will have the driver, right? So how you select a driver? Really, the driver, you gotta be look at the brake horsepower, the speed. You have 3600, 2-pole, 4-pole, 1800, 1200, and as you go down lower, then it get more expensive. Total thrust, the driver base for fit, and then discharge head, right? The discharge head have to be selected so that it can fit it with the column size below, and then have to fit with the drive ahead above it. That is the compatible with the driver base diameter, and the head is could be cast iron or fabricated. We have some flexibility options to configure a pump, vertical turbine pump. There are 8 different configuration options here. You can choose, different impellers type, open and close, coupling type, open versus enclosed light shaft, as we learned earlier. Discharge head type, I just mentioned, cast or fabricated, material type, strainer type, sealing or coating options. Now let's look at different impellers. So really in the vertical turbine pump, we have 4 different impellers here. We have air enclosed, semi-open, mixed flow, or axial flow. Notice that we highlight all of the first 3 in green, the last one axial flow. Really, the last one is basically called propeller. It's basically your ceiling fan. It's designed to move a large volume of flow and not really worry about head. The first two enclosed and semi-opens are the vanes are designed and enclosed within a shroud. The fully enclosed, they are semi-open is one closed, you want the other open. A mixed flow is really a balance. It's also open impeller, but it's a more balanced there design. And these impellers, will the connection to the shaft depends on the both side. Could be you have collets or key, depends on the both side. If you have smaller size, like for in collet summer, if it's 15-inch and smaller, then you use collet to connect to the shaft, pump shaft, and the all key for the size of 16 and higher. And it's a little bit different for the mix and export flow, 8-inch, 10-inch, and then 12-inch larger will be the key. So the next assembly, remember the column assembly, right? So here we look at the connection method for within a column and light shaft assembly, how you connect the light shaft, right? You have two methods, either threaded or keyed. Really, when do we use them? For threaded, it really depends on your shaft size. So if 1 inches to 215/16, then threaded will work really well. Anything above 215/16, you will have required a coupling with more rigid and robust design to connect these two columns. Two shafts. Now we look at the method of connecting columns. Right? We look at the way how connecting shaft. Now how we're going to connect the columns here. So for an open light shaft, really we have two major ones: the threaded or flange. Within the flange connection method, you have drop-in or within spider support. It depends on your column size, right? So if you have 14-inch and bigger, larger, then you really need, it's available in welding spider only, and anything but smaller than that, you can have a drop-in spider. All of these, either whether it's threaded or flange, they all share similarity mechanism and components. They are from 1 to 5. You have column pie, light shaft coupling, light shaft bearing, and insert bearing retainer, some kind of mechanism to support the shaft, right? But for the threaded shaft, you see the special component there is a column pie coupling for threading. The enclosed light shaft is very similar to the open light shaft to connect the columns. Instead, we have an extra component like the shaft enclosing tube number 3 there, right? Because this is enclosed light shaft, we have a tube assembly that the shaft will be housed within. And then we will have some kind of support for this tube assembly through the Spider 6, and everything else very similar method to open light shaft. Now, let's take a look at the sealing arrangement. So for an open, what we're showing here is for an open light shaft, right? Open light shaft, you rely on either pack or mechanical. So one type of sealing is packing if you allow some kind of leaking. So when in pack, you can have low pressure or high pressure. So these are some engineering design. They all share similarities, components there. Really, I want to highlight out is, for the low, these top component, this is just exploded view. Really, when it's in operation, it's going to be coming down and tied the pack 7 here. The high pressure have extra components like 14, 15, and 16. Basically, is allow some release of water through this fitting here, tubing 16, when the pressure reach above a certain threshold limits. And then because of water that you have, that's just the key difference on top of the low pressure. And if your requirement is completely watertight, then you have to rely on mechanical seal. What's showing here is just one example of component mechanical seal. You have 16 different components, but really you have the stationary phase, sealing phase, and the rotating phase below. With the component 11 tubing, you introduce a water flush line into these to lubricate the sealing phases. And this mechanical seal work rates for pressure rating from 150 psi to 425 psi, depending on the model. Now, let's talk about enclosing light shaft, right? For enclosed light shaft, the method of sealing is really depend on the rely on the enclosed tube tension kit or tube tension assembly here. So what's showing is the oil lubrication and water flush. It could be have both. For the oil lubrication, these two share similar thing. They have a shaft with a spinal groove there, allows some lubricating fluids. In the oil lubrication, you will have an oil line 5 that introduce oil into this shaft. And by gravity, you go into the spinal groove and down the shaft to lubricate it. And the water flush, you have the tube water flush line number 9 to force water into go to these again spinal groove to lubricate the shaft because the water introduced with pressure. So we need to have some kind of mechanism to seal it. So 10, 11 is just the packing and thread packing gland to seal complete the whole assembly there. And then so this one is for anything below 300 feet, right? For the column pie that greater than 300 feet, you have similar design, but what we call a heavy duty design, right? So everything has to be rigid, more components there, but they also serve the same purpose. And then the discharge head components. Let's look at it. So you have really two types, even though I showed three, really two types. Either cast or fabricated, right? Within the fabricated discharge head, you have subcategory like F, L, or T. The T fabricated head is exclusively used for canned vertical tapping pump. Remember, canned vertical tapping pump to create available MPSH. So the T fabricated head is exclusively used for canned vertical turbines, and F or L type fabricated head can be used for any types of turbines. The cast is really the cast. So it's fixed, right? You have a cast head. You cannot change any design. Everything is cast. But for the fabricated, it's a custom head. So it's really useful when your specification require vibration analysis, FEA analysis, and you do analysis and you see that you have to change your design. So the fabricated head is really allow those to happen, not the cast. Again, a little bit more information on the discharge head type. We know cast discharge head running from 4 to 16-inch sizes. I typically have a smaller class, NCB 16-1, class 1 25-pound flange. And then the fabricated steel discharge have a higher pressure rating for the flange in 150 or 300 pounds. Again, because these fabricated heads are custom heads, so they are suitable for model analysis with FEA, finite element analysis to perform on the head. For cast iron discharge head, it have it can support a column pie up to 500 feet with direct connection. If you want to go above that to the limit of 750, then you will have to rely on the steel hanger frame to support the weight of the columns. And then for fabricated discharge, because of the sturdy design there, it can by default support up to maximum 750 feet. Anything above 70 possible, but require special engineering design. In today, fast growing of CDs and TAOs across the North America and around the world, the vertical turbine pump are specifically very useful for drinking water, potable water. So for really drinking water, all you have is you need an agency regulated. So in this case, an NSF, a National Sanitation Federation for North America, their agency to regulating special material for safe drinking potable water. An example in this is that table here. Mostly you see stainless steel, which is safe for potable water, or any lead-free bronze. And if you have cast iron steel in touch with water, you will have a special coating for it, NSF certified coating. And a vertical turbine pump, NSF certified pump are great for municipal market and municipal applications, right? For supporting water to the residents of the city, towns across the globe. They're a subset of vertical turbine, so but highly regulated by the NSF agency. For sealing option with NSF, you have either mechanical or packing, same purpose, right? If you have watertight, you rely on mechanical seal, and if your application allows some leaking, then you can use relatively available and cheap option packing there. For mechanical seal, you can for the general duty single cartridge seal or standard seal is enough. But if you have sometimes you have higher pressure limits or pressure, then you will have to pivot to a heavy duty single cartridge seal. The split one you see on the upper right really is a design there, designed for easy maintenance, right? You have a split, the split design, so you don't have to pull the motor or pull the pump shaft. Everything you can do replacement of the seal easier with the cost. The NSF coating options, you have a variety of coating options, but have to be certified by the NSF again. But the two most popular one is the epoxy coating NSF and the fusion bonded NSF coating. When we use these two, for general purpose, epoxy doing fine. The fusion bonded really a special coating, which heat treated. You need an oven. The epoxy is just a spray coating, and the fusion bonded because more process and more heat involved, so it's a little bit more expensive than the epoxy coating. But the fusion bonded is required when you have a boat of both sides of 16-inch and higher, and fusion bonded just works really well. So the key takeaway for today webinar, I hope you stay awake during this afternoon time, but we finally arrived to the last slide here. Just a little bit summary for you all. Vertical turbine pump are very ideal for flood suction, deep water, high flow, high head, even low flow, low head too. They have a variety. Their envelope, as I show, can adapt to any design conditions. We have selected pump based on the system, flow, turbodynamic head, fluid characteristics, and installation conditions. The flow, just a quick tip, the flow determines the both sides, and the head determines the number of stages. We choose the right configuration, whether it's light shaft or submersible, two big category there. Within the light shaft, you can have, open light shaft, enclosed light shaft, deep set short. These are just terminologies or cam vertical turbines for the application. And we want to operate our condition near the BEP or the best efficiency point. So to maximize efficiency, reliability, and equipment life. With those proper selection, installation, and maintenance, these are very essential for a long-term performance of your equipment. Well, with that, I'm thank you for